fiber was able to connect the world or to make people close to each other in a much more efficient way.
It's enabled us to be able to Twitter or email each other or carry a BlackBerry and be able to be within touch with anyone on Earth within seconds.
If you didn't have very high bandwidth, you could not do things like YouTube or any other type of propagation of video networks. You could never do pay-at-home kind of TV. Any of those things you could never do over copper. The bandwidth just is not high enough.
I have a 4-year-old daughter. She's going to tell me how much we need optical fiber within 10 years. Imagine an empty paper towel roll. And in the inside of that roll, it's like a mirror. And at the end of that, you have a little flashlight that you're using Morse code to get the light to come and be guided out of the end.
Optical fiber is a hair-thin strand of glass.
Extremely pure, that we use to transmit signals and data over very long distances.
The light carries data, and therefore it's a communication mechanism.
Telecom, internet, voice, video.
The way optical fiber works is it's two different compositions of glass. There's an inner core glass and an outer cladding glass. All the light is contained in the inner core glass. The fact that it has two different kinds of glass is what creates the ability for the light to always stay inside the inner core glass.
We use it in submarine, underwater applications, typically to connect like across the Atlantic.
You have multiple cables connecting Europe to North America to Asia.
Increasing bandwidth from continent to continent and just really making a difference again for the whole world. And that connectivity again just brings us very close together.
The second embodiment of work would be for other long-haul applications that go across land. We would call that a terrestrial application. Once you get yourself further into the network, you get into metropolitan areas around large cities where you have a lot of optical traffic, and then eventually we'll move into premises, somebody's house, a business building, multi-dwelling unit, and then there's applications within those buildings for optical fiber as well.
It has enabled video conferencing and communications. It's enabled the entire internet and all the services that go with it. In our homes, we would not be sitting in front of our PCs at home today participating with all these great services, video conferencing and so forth, without fiber optics. It's enabling receipt of many hundreds of television channels in your home, including high-definition channels. And ironically, it is the key enabler for wireless systems. All of those cell phone towers out there connect to optical fiber, and that's how the bandwidth gets to the consumer.
If you look at the history of optical fiber, the concept of waveguide propagation, it's a very old concept. Then in the 60s, there was a race to try to find a way to do that in a very efficient way.
Corning had done investigations years before, actually, in developing what they called fused silica, which is a very high purity glass. Not quite the purity that we needed, but Corning had a good foundation of understanding how to make glass in that novel way. But they built on that and did a lot of experimentation and a lot of development on getting that last bit of purity that they needed to make optical fiber a practical invention.
The key innovation was determining a way to create low-loss fiber by creating a structure that entrapped that photon and did not let it leave the fiber as it was fired down the length of the piece of glass.
Our scientists went to work on it, and in the late 1960s, early 70s, we had developed the first low-loss optical fiber that was practical for telecommunications.
The actual design is, fascinating, but it actually took many years before you can feasibly manufacture it in large volume. Corning not only invented the fiber itself, but has invented those manufacturing processes.
It's a very high-tech process, and only a few companies in the world are capable of making a high-quality optical fiber.
When people think about glass, they usually think about sand. So I'm going to get, some sand and and put that in a furnace, and I'll get glass. Well, if you do that, you're going to get glass, but the glass is not be as pure or as clear as you need for optical fiber. You may make an optical fiber with that process, but the light will be able to propagate just a few meters, and then you don't have signal anymore.
Optical fiber is completely different. The glass is made in an entirely different way. It's a direct oxidation of chemicals to a glass in a flame, so it never touches any foreign material. So that is how the very high purity is maintained, which ultimately enables the production of optical fiber.
The first step of the process, called laydown, we take a ceramic bait rod. It's just used as a capture mechanism.
Silicon tetrachloride and other raw materials like that are delivered to the plant. We will vaporize that raw material and combust it, and that starts forming silicon dioxide.
The highest purity silica that can be produced. The result of that is a preform that's got loose particles of silica embedded on it.
As that process proceeds, then that cylinder of glass grows in diameter, and you're left with what we call a soot preform.
While we're building that layer up, we are also changing the glass composition in order to give us the index of refraction profile that we want in the final product. So the actual index profile of the final fiber is created in the very, very first step of the process. And it's very important that we never do anything to modify that profile in the subsequent steps of the process.
The next step in the process really is to consolidate or collapse or melt all those particles of silica together.
In consolidation, we do two major processes, drying and sintering.
We chemically dry it with chlorine to drive the moisture out of the preform.
And we also sinter it into a monolithic block of glass.
It's like we're baking the glass. It's not quite melting, but we're sintering the glass so that it densifies and becomes clear.
And that is called the blank, an optical fiber blank. From that point, it goes to the fiber draw, and that is where that blank is drawn into the very hair-thin fiber that we call optical fiber.
We hang the blank vertically, put it in a draw furnace, and unlike consolidation, we're actually melting at this point.
We set the blank down into the hottest part of the furnace and draw it down into individual strands. So we drop a large chunk of that glass, and the weight of that glass draws it down into individual strands of fiber.
And it is round to 99.99%, and it is the same diameter to within 1/10 of a micron over its entire length. So it's an extremely precise and extremely specialized process of manufacturing.
The most difficult part of manufacturing optical fiber is how complex the process is. You need to know everything from the glass properties when you start with that huge chunk of glass all the way down to what you're going to get optically in a small strand of fiber, and those properties change dramatically as you move through the process. So it's all about predicting what you're going to get from what you start with.
Glass has some very unique properties. It's stronger than steel as long as there's no defect. As soon as there's a defect, breaks just like that. So what we have to do is have an extremely clean environment, an extremely tight tolerance in manufacturing the preforms and then subsequently the glass. We monitor the glass as it's being drawn into fiber hundreds of times per second to ensure that the dimensional tolerances of the glass are right.
Quality it's probably the most critical piece. Optical fiber, once you install that, you are making open holes in the ground and you're putting a cable there, and you don't want to touch that cable for a long period of time. Same thing if you think about a submarine network. Imagine you have a cable now going under the Atlantic or Pacific Ocean connecting two continents, and you don't have to have a problem in the middle of that cable because it's going to be very expensive for you to go there and fix that. So that's why quality is critical.
The way Kearney understands quality is all the way from the raw materials to the use of the product, and making sure in every single step we meet or exceed our customers' expectation in terms of quality.
Quality is engraved in everyday operation of optical fiber business, and that involves research and development, and production and customer support and sales.
We have embedded, again, quality architecture into our technology, our rigorous process, and trained our people to the quality principles.
We cannot allow any contaminant anywhere in our process because a particle of iron, a particle of nickel inside of this fiber will make it non-functional. So keeping everything that we run pure and under control is really the essence of what makes this product possible.
There's several things that makes Corning optical fiber different. Starting from the manufacturing process that was invented by Corning, and every time that he invented something, you know more about that than anybody else.
Many people in the world would like to come up with low-loss optical fiber, but I don't think in many places they had the history of processes in glass that we have in Corning. So being able to pull back on work that was done in the 30s and 40s to enable this low-loss fiber, I don't think you could do that anywhere else in the world.
We have the highest quality optical fiber in the world. Part of the reason that's true is we don't buy any component of our fiber, our glass in our fiber, from anywhere else. We're not dependent on someone else to make the bulk of the glass that we'll subsequently do something to make fiber. We do it all from basic raw materials. We make all the solid substance that goes into fiber to us. We have complete control over that process. No one else has that advantage.
In optical fiber, we place a heavy emphasis on fundamental understanding, on truly understanding all the complexities of the manufacturing process. For us, I think we've turned that into a competitive advantage.
I think our success in fiber traces to a couple of things. First is our history. A deep history in materials and optics that goes back over 150 years. The next is our people. We have some of the finest materials and optical scientists in the world today working at Corning, many of whom were involved in the initial invention and still remain active today.
People ask me occasionally, what do you see in 10 years from now? I still see optical fiber. I don't see the technology that displaces the speed of light being transmitted and channeled through optical fiber for the capacity of the need in the market.
Our society is also changing the way that information is propagating and what we call information, right? 20 years ago, information was basically voice that was going through the networks. 10 years ago, it was voice and data, and now it's voice, data, and video and sound. So that's changing. And when you add those different types of media that's going through fiber, you start to require more and more capacity. So now you're moving to this distributed content generate. Content is coming from everywhere, from everybody. And that will create an exponential curve, of course, in terms of the amount of data that has to propagate into those networks. So the fiber needs to be ready for that. So that's one thing that Corning, we are working on. We have fibers already that are breaking the records in terms of capacity, more than 30 terabits per second in one single fiber. And that needs to continue. And again, as I said, a fiber is part of an ecosystem. So it's not only the fiber, but the fiber together with the equipment that goes in an optical communication system, lasers and amplifiers. All that together needs to be capable to handle that increase in bandwidth.
The telephone companies are now replacing not only those very long distances networks, but also short distances. So the telephone wires that you receive in your house, many houses in the US now and in the world, they are now receiving an optical fiber instead of a copper wire. So you are going to people's house. The fiber is now all the way to your garage door or all of that. And in the future, we see that penetrating even further, even to connect within devices and connecting in your home.
And I can imagine one day where you can go to a hardware store and buy a kit like you do today to wire your home with optical fiber instead of a coaxial cable.
There is millions, billions of people in the world that still haven't made their first phone call. And we've got to connect them into everybody else to make this global economy really flourish. I believe that optical fiber will continue to be a force to change the world for many years to come.